Good morning and welcome to your video lesson on lenses. Previously we learned that when you have light going in through a medium, changing media such as going to air to glass for example, we saw that the light rays themselves bend, and this is called refraction. So basically we're taking these ideas and applying it to kind of a practical thing that we use every day such as lenses. So what we could do is we can actually change how the light focuses with the lenses. So we'll find that we'll have these things called converging lenses, which takes the rays and kind of puts them to a focus point very close. Or we have diverging lenses, which sends the rays in all different directions. But either way, we're going to learn about how these lenses actually create an image. And then I'll take the next step in the next lesson, how we use lenses to correct for for issues with your eyes, for example. So we'll talk a little bit about that today. But first, my objectives are going to be talking about the characteristics of a diverging and converging lens. Then we're going to look at the thin lens equation, which is identical to the mirror equation. There's one or two things that are a little different, which I'll go over with you. And then, of course, the last part of this lesson will discuss how to draw the ray diagrams based on the type of lenses. So here we go. As you can see here, this is an example of a lens, but take the idea of taking one ray light and allowing it to bend and allowing it to do through an entire solid like this, and we'll find that due to the geometry of it, we'll get this thing called convergence, where we have all the light rays will actually refract and bend to a certain point right here. Actually, this is showing what is called an aberration, so the light rays are actually not all meeting here. And this is actually more realistic because lenses are not perfect. But the concept is here. So notice too that when the light comes into this, the glass here, it actually refracts twice. Because first we're going from air to glass, so then you'll see a bending of that. Now this shape is curved, which is why we see that the ray lights are actually bending in different ways. But if we follow that line coming back to that idea, it bends once into here, so you can see how this angle is different from that. Now what we do is we always take it normal to the surface, so we pretend right at this spot there's a normal line. Now you have to use your imagination at the moment, and we'll find that it does follow Snell's law to do this. Then once we're in the glass, it does the same thing. It goes from glass to air, so you see that bending again. Once again, if we take this normal line right here, if we go normal to this curved surface, we'll find that it also follows Snell's law as we do this. So this is an application of Snell's law. So here are the more perfect types of lenses that we have. We have what is called a converging lens, which focuses to a point, and a diverging lens. So just like mirrors, there are types of lenses that, like I said, converge to a focal point. And then you can see that if we take parallel rays and send it through a lens like this, they'll actually not come to a point behind the mirror. So if they don't come to a point behind the mirror, it's diverging. Now we can do what we did for mirrors and take those rays, and we'll find that actually they'll come behind the mirror to a focal point. So it's a trick just like we did with mirrors when we have a diverging case. And then the converging case, same kind of idea. We'll find that the image now forms behind the mirror. So because we need the lenses to go through the substance, what we define as real is actually going to be behind the lens, which is different from mirrors. Mirrors, we said, it is real if it's in front of the mirror, because remember, mirrors work on reflection. So the rays have to bounce in and come back. So a real image is formed when the rays are in front of a mirror. Opposite for lenses, because the lens needs to go through and refract. So the real image is going to happen after the lens. And that's the biggest difference between things that we've done previously. So notice that virtual is in front of the lens, so it's actually an image that's not really there. It's made by your brain, sorry. And then the real image is behind. So everything else in terms of terminology that we're going to be using is the same. So HO, HI, DO, DI, M, upright, inverted, all these definitions are the same. And it turns out that the equation that models these scenarios is the if I do, I die equation. And this is the thin lens equation because actually this changes if you have a really thick lens. But the same information. So F is the focal point, this is the distance of the object, and this is the distance of the image. Once again, we use the focal point to tell the equation what kind of lens it is. We use a positive focal point for a image. For a converging lens, and we use a negative focal point for a diverging lens. And then now, when it comes to distance of the image, if it's after the mirror, it's positive, and it's in front of the mirror, it's negative. So it's different here. So we just have to be careful with that. I'll definitely model some of these equations and how to work with them once we get further in the lesson. The magnification is also the same deal here. I'm just going to switch the negative sign. Sorry about that. I was trying to save time, but there you go. All right, so that's better. Hi-ho, di-do. Exact same method in terms of finding magnification. You'll see that this is the same thing right here. And then same thing right here. These are the rules that I'm going to apply to show you how to do the ray drawings, which I'll demonstrate actually in a moment. Before I go into that, I just want to show you just some features of the lenses right here. So I have the FET ray diagram. So let me talk a little bit about this. This blue line right here, this thin blue line, is the principal axis. You notice usually we put the image right on top of that blue line, because notice the object right here, the image that forms, notice the blue line touches the bottom of the image just like we have here. Now you can move it anywhere on this plane, but notice that gives you the middle of the object right on the middle of the principal axis. And vice versa. If we did it like this, it certainly works. But notice the beauty of putting the bottom here is we know the size of the object. Because if I put it right here, technically the rays will cross right at the principal axis just like I have right here. But I don't know how high to draw this, so that's kind of an issue. So this is why we put it like this. Okay, so let me play with a couple things. First of all, notice that I'm only going to be dealing with the converging lens because I don't have the option for the diverging lens. So think of a magnifying glass. This is exactly how a magnifying glass works. So with that kind of in mind, watch what happens. If I bring the magnifying glass, and by the way, I'm sorry, these are the focal points right here. And actually I could move these if I wanted to, but for now I'm just going to kind of leave them there. So notice that the further away this is, the smaller the image becomes. So if I take a magnifying glass and pull it away, the image is going to get really small. And then, because it's the opposite, if I bring it close, it's going to get really big. And you can see that that's true. In fact, right to the focal point, this thing's get pretty large. Now, of course, it goes off the screen, but that's all right, like this. Now, just like before, if we're on the focal point, notice these three rays do not cross and form an image. So once again, the focal point issue works. So right past the focal point, notice these lines start to get really far apart, and they'll start to actually converge past the focal point, which means the image happens in front of the lens, which makes it virtual. So here we go. So notice that just like a magnifying glass, right near the focal point, you get a huge magnification, hence the magnifying glass. But if I took a magnifying glass and put it as close to the image, notice it barely distorts the image, like this. So with a converging lens, notice some of the traits too, right? This is inverted and smaller, but as I get closer, so it's still inverted up to the focal point. But once I go past the focal point, it flips, it's magnified, and it's upright right here. So you can see that here. All right, now a little bit about the ray drawings, because I'm going to be drawing these very soon. So the three principal axes work very similar to what we've done before. Principal rays. I'm going to do that. So here are the three principal rays that we're going to deal with. It's actually modeled here, and of course I'll draw them. So the first ray, if the parallel ray goes through, so a nice straight line goes through, by geometry, what's going to happen is this ray is actually going to pass through the focal point on the other side. So we need to know the focal points on both sides. And it's symmetric, so whatever the focal point is here, it's going to be the same right here. So that's our first ray. And it's going to go through the focal point. Now we always draw it from the top of the image, just like we have here, so that we know where the top of the image is down there. The second ray is kind of like the mirror one, except we're going to go through instead of bounce off. So if we pass through the center of the mirror, exactly through the center, we'll actually pass straight through. Now, that's because right at the center of the mirror, we're going to pretend it's flat, like not curved. So if that's true, what we're going to assume is that the Snell's law that works here, and it's flat on the other side, it doesn't, Snell's law works, but it doesn't distort or bend the light. So we can draw it right through the center right there. And then lastly, we have this up here, and it's kind of the reverse of this. So if I start off going through the focal point, it's going to come out straight. And notice to form an image, we need 3 lines to, well, technically it's just 2, but notice 3 lines right here connecting like that. So I'll draw a few things to show you what it looks like. Some other features to just, kind of consider, because this is good to show you. So the curvature, so the more round this becomes, the more that it's angled and the more bending of the light. So in other words, this image will get closer if I start to increase the curvature. Oh, I'm sorry. I was thinking the opposite. So here we go in this case that we see that the image gets closer when I reduce the curvature. I'm sorry, that's because it looks more curved here. And this is becoming more flat here. So you can see that. Sorry, I was actually thinking of this case when I was talking about it. So actually, let me restate that. So what you have here then is as you increase the curvature, we're spreading out those lines a lot more, which means we're going to get a much bigger image. And this is reducing those lines in the bending, which gives you smaller. So that's the curvature right there. So when it comes to refractive index, remember refractive index means how dense the material is. So the more dense, the more bending. So you'll see that this is true right here. See? So if I increase the refractive index, it's going to bend the light more, bringing the image closer. And then this is the opposite case, as you can see here. Now the diameter is actually what's important in astronomy. So one of the biggest things in astronomy is being able to see faint objects. And it all has to do with the diameter of your lens, and mirror technically, because more light, you can get fainter objects. So if I reduce the diameter of this, notice that this gets dimmer. And then if I increase the diameter, it gets brighter. That's because if we look at the many ray approach to this, I reduce the diameter. Notice with only 2 rays, I get a very faint image because I only have 2 light rays coming in. But as I collect more rays, you can see it actually gets brighter. So astronomers really care about this because the bigger the lens or mirror, the more light, which means we can see fainter objects. So that's why things like the James Webb Space Telescope, which is being launched very soon, is a pretty big deal in astronomy because it's humongous, which means we can see deeper into our universe, which means we can see fainter objects, all these kind of cool things right here. So the diameter changes the quality of light, and of course can allow fainter objects if you have a big diameter. Okay, so enough playing with this. Let's see what I have here. Okay. So, which one do I have? I have all the objects. Okay, so we're going to do that, what this says right now. So I'm going to practice drawing the ray diagram, but I'm also going to calculate the values just to show you that it does work. So I'm actually going to use this one because I want a little more space. Alright, we'll just try to do that so it's a little better. Okay, so same thing that we did for mirrors. So I'm going to do B for no particular reason, just because I have 3 of them right here. So I'm going to model how to do B. So the first principal ray, so I'm going to, because this is on a graphing a graph paper and the B is right in the center, I'm going to start right in the center of the object right here. So the first law says that if I start at the top of the object and go straight into the mirror, then my refracted ray will go straight through the focal point like this. Just like that. Now notice I'm a hair off of the line right there, but that's okay. But that's our first principal axis. Now remember we're refracting, so we're going in and through. And notice that even though this thing is actually curved, I just started on this line right here just to make things a little easier. The second principal ray says that if I start, right here and I go through the center of the lens, then I'm going to actually stay going in that same angle, same approach through the center right here. So I'm going to try to make the angle the same. That's about right. Like that. Now, I know my image right now is being blocked. I'll move it down so you can kind of see it right here. There we go. So you can see that we're forming an image right here, or going to be forming our image right here. And quite technically, remember, you only need 2 rays, so you're done. But why not? Let's do the other one too. The other one says if I go through the focal point to the mirror, that I will pass straight through on my way out. Just like that. So those are the principal axes. And then, of course, it's when the 3 of them actually converge that we'll get, an image. So you can see I'm a little off, which is fine. In fact, I think my blue line's off just because I couldn't see what I'm doing. I actually trust these 2 better. But either way, I'm just going to average it out right here because that's about where they are. Now remember, that is the top of our image. So remember, this is where the B is. So this would be our image right here. So that's our B, just like that. And actually, this totally works with what we saw. We saw as you get closer to the focal point, and you're in front of the, well, I call this the front of the, if you're behind the focal point, and over here, you're going to be inverted, and as you go closer, it's going to be bigger. So basically, I did this case right here. And that looks pretty much what we have there. So you can see that we'll make according to this diagram. So it's behind the lens, which means it's actually real. So it's behind the lens. Now notice it's upside down, so because it's upside down, it's inverted. And notice that more or less we're, instead of 2 boxes for the height, we're 3 boxes for the height. So notice that because our size is greater, we are magnified. So bigger, we're magnified. Like this. Okay, so that's for B. Now I'm purposely going to go and draw C, and then I'll verify, actually I'll verify with calculations, and then we'll draw C and verify with calculations. So real, inverted, magnified. So mathematically we should see that this is true. Oops. I'll come back to that. Perfect. So now what we're going to do is use the thin lens equation. If I do, I die. To verify that what we just did with B works. So the focal length, according to the question, is 3 centimeters. Now we're a converging lens, which is a positive focal point, and says letters A, B, and C are placed at the following distances. So A is 8 centimeters, and B is 5 centimeters. So because we're looking at B specifically, The distance of the object is going to be 5 centimeters. And let's verify DI, and we'll find magnification. Okay, so 1 over 3 centimeters, because converging, equals 1 over 5 centimeters plus 1 over DI. So let me grab my calculator. So I'm going to do my math. So 3 inverse minus 5 inverse, inverse. So I hope you don't mind, I just did this mathematics pretty quickly. So I moved this over, subtracted the 2, and then I found the inverse of that. So DI I got as 7.5 centimeters. So let's verify that. So notice that, this is technically drawn to scale. So from here to here is 3 centimeters. So actually, a little bigger than 3. Or 4 maybe. Yeah. I'd say this is pretty accurate. Yeah, that works. About 7.5. So that works out. Cool. So, check. Now notice the answer is positive, which makes it real. And that also checks out. Now let's verify magnification. So we negative di do. Let's do that. So di do would be negative 7.5 because our image of the object is actually real. And the distance of the object is 3 centimeters. So negative 7.5 divided by 3 gives us the following answer for magnification. So negative means inverted. Check, because we actually did get an upside down image. And this number is bigger than 1, which means it's a bigger image. Check. That's exactly what we said, real, bigger, inverted. So the calculations do work. So let's go ahead and do C so you can see what happens when you're in front of the focal point. So same kind of setup here. I'm going to draw the same thing. But notice that we have a little complication because of the placement of C. So the first one, let's go this and let's do black. Still works. So start from the top of the image and go right into the center there. And then we pass through the focal point if we go in parallel. So I'm going to go ahead and do that as best as I can. There you go. In fact, I'll do this a little bit. Now remember, this, if you remember from the diagram, the FET thing that I was doing, this is actually going to be inverted and real, but we'll see what happens. So the next thing I'm going to do is do the fact that this thing will go through. Now, because I just want to be pretty accurate here, I'm just going to do this for now because this is actually going to make it a lot more accurate. So notice my in goes through the center and it just keeps going. And if you notice right now, this and this is technically a dotted line. Let me just draw it right on top or right next to it so you know that this is in fact a dotted line. Now I'm just going to explain why I'm doing this. So this is actually the refracted lens part, but I only kept the solid line so I have a more accurate measurement as I do it. So just like with mirrors, if these two lines don't converge after the lens, we have to go behind the mirror. So what I'm going to do is exactly that. So I'm going to take my ray and just trace it back on top of that line as accurately as I can, because obviously when you do it with a pencil this will be pretty accurate, but with this computer I'll do as best as I can. So I'm going to take that line and do that, and then I'm going to do the same thing with this line, and actually I'll use the focal point as a place for this. And there we go. So there you are. Once you have 2 points, you can go ahead and draw that in. Now notice that you can't really do the third one going through the focal point, because technically if we go backwards, this thing will never actually converge. I mean, you could, go backwards like this and then come out, but I'll just say it just doesn't work. So you're only limited to 2 in this point, but you get enough information to see that it does get bigger upright like this. So that would be our C. So let's go ahead and verify with the calculation just to show you that this is actually true. Oh, before we do, notice that this is, first of all, it's virtual because it's in front of the mirror. It's upright because it's the same direction, and this is bigger because it looks visibly bigger than C. So now we're going to verify with the equation. So here it is right here. Same focal length, it's positive because it's a converging lens, but now our distance of the object is 2 centimeters. Solving for DI, I'll do that quickly. 3 inverse minus 2 inverse, and perfect. -6 centimeters. So this is really good because the negative sign here means it's virtual. So, and that makes sense because if this is our focal point at 3, about 3 right here, it's roughly about 3 over here. So this kind of works out nicely. So this actually does check out. And then the magnification, negative DI over DO, will look like this. So -6. And then we have the distance of the object, so which was 2 centimeters. There we go. Sorry, I didn't find it. The negatives cancel, so basically we get 6 over 2, which is 3. So positive means upright. Check. And m greater than 1 means bigger. Check. There you go. So this is how you do the ray drawings for the converging lens. Remember, you only need 2 of the rays as you do this, so you don't need 3. So it's okay if they're a little off, as always. I'm not looking for perfection, but I am looking for concepts and understanding. So if yours is a little off like this and you just put it in the middle or here to here, that's totally fine. What's not fine is putting it over here, putting it up here, putting it over here, putting it way over here. So obviously you have some understanding of this with that. Okay, so those are for converging lenses. And I think at this point I'm going to stop the video just to cut it off a little bit and do the next video with diverging lenses. Oops. I will shut it off in a moment. Gotta find my mouse. Okay. Alright, I'll see you in the next video with diverging lessons.